So solenoid and a battery. So you have to draw 3 magnetic fields to show the direction in and around the solenoid. So if we use the Knuckle Rule, where we check that the current's going up, so that means for the outside, the magnetic field, is going out this way, but on the inside, it's going the other way. So on the inside, it would be going this way. I'll just draw that a bit clearly. Yeah, and the point to be careful about is that you don't intersect any of your magnetic fields, because then that would be wrong. So this is a loop and it has 3 turns, current, blah, blah, blah. What's the magnetic flux through the loop? So flux is, through the loop, currently, like, as we saw before, the field goes this way and this way. So that means, sorry, is this the wrong way? No, sorry. So that means the plane is parallel to the field line, so there's no flux, and that would be plane parallel to field lines. So draw the force on side PQ. So PQ is here. So the current we know is going this way, so it's coming out of the page, and the field is going to on the inside, it's going to the left. So if you use the right hand rule, so current is coming out at you, the field is going to the left. So the force is going down, so you just draw a down arrow. And that's question 3. So what's the magnitude of the force on side PQ? F equals N I L B. So N is 3, I think, from the information at the start of the question, 4 times 0.04 times 5 times 10 2, and you just get 0.24, which I'm going to write with scientific notation. So what is the force and the magnitude on side QR? QR is this side, so again, that's parallel to the magnetic field, so it's 0. Side QR parallel to field. Question 6. Which one best describes the voltage on the I don't know how to say that, but if you look at it, it's generators and alternators. And so the first thing we check is, well, you could just look at the general graphs and you know it's not going to be C, because it really wouldn't be the same. And PQ, and you can see there's slip rings, so the output is going to be AC, so it's not B or C, so the only answer is A. So explain the difference, the function between the slip ring commutator and the split rings. So if I write it really shorthand, so split rings, reverse current every half turn allows torque in constant direction. And they don't say whether this is a generator or a motor, so I'll just write allows for DC output if needed. So slip rings, how they work: maintain current in one direction, prevent like tangling, allows AC output if needed. And next question, so question 8, sketch voltage across time. So we have the flux graph, but we know that voltage is negative, delta phi on delta t, so this is a positive gradient, then our graph has to be negative because it would be negative with the explanation. So it would be like this, except use a ruler. I'm not using a ruler, but use a ruler. Make sure that you they can see that this is Lenz's physics law. So you can write Faraday's for the whole equation, or you can write Lenz. I think the answer is accepted both, and I think they also accepted if you just wrote the equation as well. But yeah, if they're asking for a law, I think you probably should write the name. So the magnetic field is reduced to 0 over a period of 0.012 seconds. What's the average EMF? So EMF is negative n delta phi delta t. We can ignore the negative, but other than that, it's 120 times 3 times 10 to the negative 4 on 0.012, which is 3. So the field is being reduced. Which direction will the current flow through the ammeter? And I got Q to P. So that's because, so the original field is to right. So when it's reduced, field to right decreases, hence flux decreases to right, and then using Lenz's law to oppose change in flux, induced flux increases to the right. So then if you look in the loop, if the flux is coming out here, so the field lines are coming out, you can tell that the current is going this way. So it's going this way, and you can see if you follow it, it's going from Q to P. So flux increases change to right, hence using right hand grip rule, current flows from Q to P. So next question, when the heater is turned on with only one element connected, what is the power output? So power is just P equals times V, and it has two identical heating elements with constant resistance of 48, so we can rewrite this as V squared on R, and V is 240, and since there's only one element, then we only use one part of the resistance, so it's 48, and that simplifies to 1200. Complete the circuit when the heater is set to provide a heating power of 600 watts. So if it's 600 watts, then we have to calculate how much current is going through here. Equals 600 divided by 240, and you get, I didn't write this down, but let me see, 10 on 4, 2.5. Yeah, 2.5 amps. So then you have to calculate how the circuit would be flowing. So it could either be running in series, or it could be running in parallel. The easiest one to check would be series. So if it's series, the total resistance is just the addition, so it's 96. And then I equals B on R, so 240 on 96, and that is 2.5. So since they match, you have the current that you want, so you know it's going to be corrected in series. So there's transmission lines to the globe, negligible resistance. And initially, the power supply is 2 volts in DC, and they find that the light does not glow as brightly as they thought. So that's because of the transmission lines. So I said current flows through transmission lines, resistance causes power loss. Less voltage reaches globe, hence globe shines less. So that's that one. Question 15. The voltage setting of the power supply is set that to the globe operates at 4 volts and calculate the voltage of the power supply. So I just drew like a little circuit thing that's probably missing a lot of the notation, but so 4 volts, so P equals so I times V, and I we don't know, so P on V is I, so 4 and 2, I is 2 amps, and then so V drop is what's lost in the power lines. So this I times R, and that's 2 times 4, which is 8. So then the V that from the power supply is the voltage here, and then my added on to the voltage that we lost. So it's 8 plus 2, which is 10. Next question. The globe is operating at 4 volts, and what's the power loss? So P equals I squared R. I, we know is 4. Oh, sorry, I actually did. I times V, and I is 4 times, I'm writing this wrong, 2 squared times 4. There we go. So 16. I we got from here, and R is the addition of these two. So explain why AC is used for long distance electric power transmissions. I just said, oh, that's because AC can have delta phi, which is needed for induced EMF used in transformers. Can't use DC. This is a really shorthand version, but like you have to write this more coherently, I guess. And then you have to explain like increasing the voltage in power lines decreases the current, so less power loss. And that's modeled by the equation P equals I squared on R. So I decreases, then P decreases. So question 8. There's an AC system and they modify it. So now there's a transformer and they're testing the power supply and connecting to an oscilloscope. So what's the signal they will observe? So since this is AC, the voltage that they gave us was RMS, and that was 20.8. So that's not the actual like peak value, because that would be like, that's this one, 20.8. What we're after is this one, or like if you're checking these answers, it's the 2 times that value. So to get V peak, it's just 28.8 times root 2, which is 29.4156. So the only answer that's there is C, but C is from peak to peak, and that's not correct because this is only VP. And V peak to peak would be 2 times this value, which is 58.83. That matches D, so that's why the answer is D. Question 19. So it's a 10-to-1 step-down transformer, and the input has 1460. So since the turns and the step-down, like the ratio are related, you can just use this, but you can just tell it's going to be 1460. So for the previous experiment, what's the power loss? So I figured out what the current was by using the current at the globe. So P equals I times V, I equals 4 and 2, which is 2 amps. And then I figured out what the current in the transmission lines was. So that's N2 on N1 equals I1 on I2, and I solved for I1. I got 0.2, oh sorry, I2, I solved for I2. I got 0.2 amps, and then P loss. So this is, you use this for I1, and then P loss is I squared on R, so that's 0.2 squared times 4, which is 0.16. And that's electric power. So interactions of light and matter. So you have to name 2 experiments that support each of the models. So the 2 experiments we know are the double split experiment and the photoelectric effect. So for the wave model, that's supported by the double split experiment. And I said diffraction of 2 waves from the splits shows interference, and then I said interference was a wave property. Was a wave property. I put more detail into it. I'll just read out what I actually wrote. So I wrote, by shining a light through the 2 slits of a flat surface, diffraction was seen at the slits, causing a set of new wavefronts to be formed, and then and 2 spots of new wave propagation. Then the waves from the 2 places of interference cause bands of white and black lines on the end screen, which are due to constructive and destructive interference. And then I said that the interference seen in the bands is a wave property and hence supports the wave model. So, like, yeah, write it in more detail, I guess. The particle model is supported by the photoelectric effect. Oh, sorry, this is I'm thinking of another question. So this is the one that supports the wave model rather than the particle model, but since it's 3 marks, you might want to mention why it doesn't support the particle model. So particle model would hypothesize that only 2 bands formed opposite to the placement where the slits were, not observed, hence not supported. So what I actually wrote was, the particle model suggests that only 2 slits of light should be seen at the locations in front of the slits. As this was not seen in the experiment, the particle model was not supported by this experiment. This question, so as I said, 2 is the wrong one because for how the particle model explains this. So particle model states that f must be greater than f0 in order to overcome work function of the metal. So write something like that, and then maybe mention the wave model predicts any wave can reject an electron. Yeah, it probably, I didn't write it because I got this question wrong, but like detail, yeah. Question 3. So there's a photon. So photon of the light in the laser. So this is not a particle, like a particle with momentum yet. So we use the de Broglie wavelength, and since the answer's in electron volts, H is also in electron volts. 580 times 10 to the negative 9, so that's like 2.14. So that's this question. Path difference from Y to the slits. So path difference is just Y, oops. Y is a dark band and X is a bright band. So what's the path difference between S2Y and S1Y? So Y is dark band, so we use this formula, but we don't know lambda, so we have to use this part that they gave us. Equals n lambda 1160 equals, and X was the 1, 2 second band, so n is 2. So lambda is 580, and then we sub that in here, so PD is, and Y is the third band, so 3 minus half times 580, which is 1,450. So photoelectric effect, usually they'd have like a line here and that would be a work function, but there's no scale, so there's no point in drawing that. So students double the intensity of light, which the following graphs show the results. So intensity does not affect the kinetic energy, so there would be no effect, so it's D. Which of the following? So now they're using a work function less than the original work function. So we know the work function is the y-intercept. So if it's lower, that means the graph should move up. So that means it's A. And the explanation, I wrote EK max is HF minus W, and work function acts as vertical translation. If work function decreases, then graph moves up. But you have to mention that H is constant, so gradient of new graph has to be the same as the one of the old graph. And now we're at diffraction of electrons. So de Broglie wavelength of the electrons, but this time we have to, they're like particles, so we use H, lambda equals H on P. So lambda equals 6.63 times 10 to the negative 34. And they tell you the speed, which is nice because we don't have to use that square root 2 MEK1. So 9.1 times 10 to the negative 31 times 1.5 times 10 to the 7. And you get 4.857 times 10 to the negative 34. So we round it, it's, oh, sorry, 11. Negative 11, but that is in meters, so we add like times. we make this times 10 to the negative 2 times 10 to the negative 9. So then if we take it as 10 to the negative 2, you get 0.0, so 0.0485, because it's in nanometers. Oh, maybe I should round it. I'll just round it. So question 8, explain. So they increase the voltage and hence the speed. So they're asking which diffraction pattern it would be. So you can see the difference here is the gap between the two circles. So the answer here is A, because we know from the equation we just used lambda equals h on mv, and lambda is the thing that determines what this looks like. So if v is increased, so v is increased, that means lambda is decreased, and then since spread is proportional to lambda on w, if lambda decreases, that means spread decreases. So that's why you see less spacing. So explain where the X-ray is produced. Very similar patterns, obviously because of the wavelengths. So I just wrote both diffract with different energies. But same wavelength. Same wavelength means same diffraction. Hence, similar pattern is seen. So the energy of a photon. So what's the answer for this? Is E equals H times F. Yep. So E equals HC lambda, which is 4.14 times 10 to the negative 15, 3 times 10 to the 8 on 478 times 10 to the negative 9, which is, oh, sorry, I'm doing the next question. Let me just move this. Cut. Oh, well, that didn't work. Anyways, I'll just redo this question because I was doing it wrong. So, the two things we have. Sorry. The two things we have are the energy of the X-ray and the energy of the electrons. So E equals hc lambda. That's for the X-rays, and the other one is E equal. Oh, we'll just work with the electrons to find lambda. So hc on E, but we have to convert this E to, because they gave it in electron volts, you have to convert that to joules by multiplying by 1.6 times 10 to the negative 19, which is the charge of an electron, and then you get lambda. And then the next thing you do is you use lambda equals HP, and this is for the photons, the electrons. So lambda equals H on. So for P, we get MV. So EK equals half mv squared, because we need energy in the equation. So 2ek divided by m, and then when you sub it into here, the square root m, it would just become 2ekm, and then you can put that under here, and then you use this lambda, that you found here, and you know m is the mass of an electron, and I didn't write my in between steps, but you get lambda is 2 point, oh sorry, you're not trying to find lambda, you're trying to find ek, because you already know lambda. Lambda is this one that you saw from here. So ek is 2.4 times 10 to the 4. You actually get answer in joules here because we used kinetic energy. That's why we had to convert this one to joules. But once you get this answer, you should convert it to electron volts because that's what the question is asking. Next question, which is what I did earlier. So the wavelength of this, the measured photons transitioning between the two states. So to know which state it starts on and goes to, we have to know how much energy there is. So E equals hc on lambda, which is 4.14 times 10 to the 15, 3 times 10 to the 8 divided by 478, 10 to the 9, you get 2.6. So we're looking for a difference of 2.6, and that's this one. So yeah, I think that's the last question. Yeah.